Okay, so welcome everybody, and welcome everybody who is actually looking at this talk via the YouTube channel. It's an absolute pleasure to have with us Andreas Efstathiou, from a rector of the European University Cyprus in Cyprus. He's one of the experts on the modeling of spectral energy distributions of galaxies. Andreas obtained his PhD at Queen Mary University of London on the topic of radiative transfer in axisymmetric dust clouds. This was with the supervision of Michael Rowan Robinson. This was followed by postdoctoral assignments at various places, University of Hertfordshire in Hatfield, also Imperial College London, after which he joined as a professor at the European University of Cyprus. He was also part of the HERschel Extragalactic Legacy Project and coordinator of an ESA-funded project called Cygnus, the Cyprus Models for Galaxies and their Nuclear Spectra. So it's a great pleasure to have him give a talk here in this J1 Commission. And his talk is going to be today on spectral energy distribution fitting with radiative transfer models in the James Webb era. So thanks so much. Take it away.
Okay, thank you very much. I would like to, first of all, thank the chair of this committee for inviting me to give this presentation, this seminar. So I'll just share my screen. Share. Put this in presentation mode. Okay. So can you see my screen?
Yeah. Yes. Yeah, I can see. Thank you.
Thank you very much. Okay, so I've chosen as a title of my talk, Spectral Energy Distribution Fitting with Radiative Transfer Models in the JWST era. We live in a very exciting time. We have very good data from James Webb, but also from a lot of other missions still exploiting data from Spitzer and a lot of other facilities. So let me just outline here a few challenges we are trying to address with this kind of approaches. This is my personal preference. It's probably not a complete list of challenges. So what we are trying to do here, we are trying to understand the physics of star formation in galaxies across the whole history of the universe. We have local galaxies we are studying, but also increasingly galaxies at very high redshifts. We are trying to understand the physics of accretion onto supermassive black holes in active galactic nuclei, understand the environment of active galactic nuclei, again, during the history of the universe. We are trying to understand how feedback from AGN affects the shaping of galaxies and regulating star formation. We are interested in understanding the star formation and accretion history of the universe. We are interested to understand if the observational picture agrees with predictions from cosmological simulations and other models of galaxy formation and evolution, such as semi-analytic models. And the interesting thing is that all of these challenges, to address them, we need to gather, obviously, data, but also interpret the information encoded in the spectral energy distributions of galaxies. And this is mainly the topic of this talk, to develop methods for interpreting the data. Traditionally in astronomy, we are looking at images, which we see, for example, on the left here, the famous radio galaxy Centaurus A, which is a dusty galaxy, as you can see. We can also see some radio jets, but we cannot, from an image like this, address questions like, what is the star formation history, star formation rate of this galaxy? What is the stellar mass? What is the contribution from an AGN? To address this kind of question, it's better to look at a plot like the one on the right, which we are all familiar with, the spectral energy distribution. This is from a paper we did back in 1999 with David Alexander as the lead author. And even 25 years ago, we could attempt to separate the SED, to decompose the SED, if you like, into three components: the AGN torus, we see pointed here with the blue arrow, the starburst model, and the host galaxy model. So even 25 years ago, we had good, reasonable models for all three components. We have a lot more now. On this slide, I'm trying to illustrate how useful the analysis of the SEDs is for studying very high redshift galaxies. We see a galaxy here discovered in the HELP survey, and we presented this in 2021. It's impossible you can barely see the galaxy onto these images on the left. But with the spectral energy distribution on the right, we can do a reasonable analysis of the SED by decomposing again into the different components. And we can see this is an object which is dominated by the blue curve, which is the AGN component. And we can infer the AGN fraction, but also the star formation rate, stellar mass, and so on. Okay, we're interested to study, as I said, the AGN environment. It's virtually impossible to resolve this environment, even with the best telescopes today. So a very useful approach would be to have models for this component. And we have a number of models for the AGN torus and generally the AGN environment, and try to feed SEDs and infer the properties, which this is one of the things that I'm going to try to demonstrate here, that by trying to feed an SED of a particular object with different models, you can infer which model fits better the observations and therefore infer the properties of the obscurer. Going to galaxies, this is the famous diagram of the star formation rate versus stellar mass. Obviously, there's a lot of this talk of this main sequence and galaxies lying above the main sequence being characterized as starburst. But obviously, to be able to plot a diagram like this, you need a good estimate of the star formation rate and stellar mass. And these kind of techniques using SED fitting are crucial for this. This is for AGN feedback. Yes, as we all know, you need AGN feedback to regulate star formation and prevent the formation of very massive galaxies. And by estimating the AGN component in distant galaxies, you can try to understand this the effect of feedback. On this slide, we see the discovery of submillimeter galaxies back in the late 90s. This is from the paper in Nature. We see the scuba image of the Hubble Deep Field, which was obtained on the James Webb Space Telescope. And even back in the late 90s, we could use radiative transfer models to infer to make the first predictions about the redshifts of these galaxies. And on the right, you see a first attempt to fit an SED of the most distant, the most bright galaxy in this field, HDF 851. We now know that these very luminous merger submillimeter galaxies appear to be much more numerous than predicted by semi-analytic models. We see a comparison here with the Galform model. As far as the star formation history of the universe, we have a good understanding of the history up to redshift 2, but there are a lot of uncertainties at high redshifts, and but all estimates of the star formation rate is crucial for characterizing this formation history. I'm going to present some results from a project. We were involved, the HERschel Extragalactic Legacy Project, which has cataloged 170 million galaxies out to redshift about 6. And this is one of the best databases for studying galaxy evolution out to high redshifts. Of course, we have very nice data from Spitzer, and now increasingly from the James Webb Space Telescope, and we are trying to incorporate this information into the kind of analysis we are doing because it's very crucial for constraining the properties of galaxies. We can see here galaxies separated into ULIRGs, the black line, which have strong PAH features and deep silicate absorption, quasars with red, with silicate emission and no PAH features, and things in between. All of this information we think is crucial for constraining the properties of galaxies through SED fitting. And as I said, it's very interesting to try to include some of these radiative transfer models I'm going to describe today into simulations of galaxy formation such as Eagle, Illustris. And there are a couple of attempts to do this. For example, I think the most successful ones were from the group of Martin Baez and Ghent, a couple of papers, Camps et al. And I think this is an approach which can allow us to go from the simulations to observe quantities we can compare with the observed universe. So just, I know this is a group that understands very well why we need a multi-wavelength view of galaxies, but let me spend a minute or so to make this clear. There are three main types of activity in galaxies. You have star formation in quiescent disk galaxies like our own. When we have bursts of star formation in starburst, when these quiescent galaxies interact or merge. And we also have accretion onto a supermassive black hole, which is activated by processes like this. All of these processes are associated with a lot of gas, but a small tiny amount of material in these clouds is in the form of dust, which is much more opaque than gas. And so most of the interesting effects, if you like, in terms of radiative transfer are due to the effects of dust, which absorbs the optical and ultraviolet radiation and re-emits it in the infrared from 1 to 1,000 micrometers. So if we are really interested in understanding the energetics of galaxies and inferring their rate of producing stars, their stellar mass, their age and fraction, we need observations of galaxies from about 0.1 to 1,000 micrometers and models for their emission, ideally radiative transfer models which encapsulate better the physics of the interaction of light with dust and its re-emission. And I think it's also central to say that we also need good methods for comparing efficiently the models with the data and estimating physical parameters such as the stellar mass, the star formation rate. We can also estimate the supernova rate, and we've done this in some examples, some galaxies. Now, let me try to answer the question, why do you need to do this with radiative transfer models, which are, as we know, difficult to calculate? The radiative transfer problem is a computing intensive problem. So why should we use these models and not try other methods? As we all know that we have a plethora of SED fitting codes like SIGAL, McPhee, Beagle, Bagpipes, Prospector, HNFitter, and so on, which do not rely on radiative transfer models. They rely on something which is called energy imbalance method. I think I already gave the answer is because it's more, you include more of the physics of the galaxies if you use the radiative transfer models. And what we have demonstrated in the last couple of years is that you can actually do SED fitting with these models in comparable time to energy balance methods. We had a paper in 2022 where we modeled the HERUS sample of ultraluminous infrared galaxies. And we had a paper this year, Varnava and Efstathiou, which presented another second method, MCMC method, for doing this. Now, the key feature of our method is that you don't actually compute the radiative transfer model in real time, on the fly, as you do the fitting, but you compute pre-computed libraries of radiative transfer models for AGN tori, starburst, and host galaxies. And you actually interpolate these libraries during the fitting by varying all of the parameters to get the fit. And this works very well, and I'm going to show you lots of examples later. We think that this kind of approach can improve even further by taking advantage of AI, which can accelerate the calculation of the models. And I'm going to discuss this a little bit more during the end of the talk. Now, we've been doing SED fitting with radiative transfer models, as I showed the example of the Sene for a number of years. In the last couple of years, we put all of this activity under a project called Cygnus, which stands for Cyprus Models for Galaxies and their Nuclear Spectra. This is a project which is funded by the European Space Agency. And so what do we do here? We assembled various libraries. We either computed ourselves, but also libraries computed by other people, especially for AGN tori. And we plan to include more libraries. And then we develop MCMC methods for fitting the models to multi-wavelength data. We think this approach is going to be very promising for analyzing multi-wavelength SEDs of galaxies from a number of ground-based and spaceborne facilities. As you can see, a number of interesting telescopes, Spitzer, HERschel, and James Webb here. So these are the models we use at the moment within Cygnus. For the AGN, we have 4 different models. We have our model on the left, which it's a tapered disk model developed back in the mid-90s, and we computed recently a library for this model. We have the Fritz model, Fritz 2006. Both of these models I just mentioned are smooth models. The distribution in the torus is smooth. But we also included 2 other models which are two-phase. You have clamps included in a smooth medium. We have the Skertor model developed by Stalewski et al. 2016, and the Siebenmorken et al. Model developed in 2015. The Skertor, the 3 models use a normal interstellar mixture, whereas the Siebenmorken model assumes fluffy grains which have higher emissivity in the far infrared and sub-millimeter. So our approach allows us to explore 4 different AGN models. We have a single starburst model at the moment incorporated into this framework. The starburst model developed by myself and Ralph Siebenmorken and Michael Van Robinson back in 2000 and revised in 2009. We have a model for polar dust, which is at the moment is a very simple model. We just assume spherical clouds which we have the same temperature for all of the grain species, but we still solve the radiative transfer problem in a spherical cloud. This is an area where we may improve. And on the right, we have the host galaxy models we use at the moment. We have libraries of spheroidal galaxies, first presented by Efstathiou 21. And we have disk models in a paper which is still under preparation. But the important thing to know here is that the models on the left, the starburst, polar dust, and AGN models, we are assuming that we have the same library at all redshifts. We are starting here. On the models on the right, we assume a different library for different redshifts, but this is all done automatically by the fitting code. Okay, just a few words about the starburst model we use here. We incorporate the stellar population synthesis of Bourgeois and Charlot. We do radiative transfer with multi-grain mid-size mixture, which of course includes the effect of small grains and PAHs. We use the model of Siebel-Morgan and Krugel. And the one important innovation of this model is that you have a model for the evolution of giant molecular clouds that constitute the starburst. And it's better to illustrate this with this diagram here. Assuming you have an episode of a starburst lasting 30 or 40 million years, you don't, obviously you have some star formation history in the starburst, which we assume it's exponential. Okay, the molecular clouds that constitute this starburst are not all assumed to be the same thing, the same structure, but we have a simple evolutionary model for the molecular clouds, which basically allows you to model the transition from an H2 region into a PDR, which may have a completely different spectrum. And so this model, assuming a star formation history and these computations of the giant molecular clouds at different stages of their evolution, you can predict a different spectrum for a starburst at different ages. Okay, moving now to the AGN model, we use the first of the AGN models we use here. Okay, on the right you see this very anisotropic emission from the torus. One key feature of our approach here is that we take into account this anisotropy of the torus to correct the luminosity of the torus. When you feed an AGN with one of these curves, which of course we have a number of these curves because you have a library, you cannot just integrate over frequency and then multiply by 4 pi dl squared to give you the luminosity. You need to take into account the fact that the emission from this torus is emitted anisotropically. We quantify this with this anisotropy factor, I list here, alpha, and this is just the ratio of the luminosity. If you just integrate the luminosity over inclination divided by the luminosity if you just assume that the thing is emitting anisotropically. And as I'm going to show, this anisotropy factor can be up to a factor of 10. If you are observing something which is more or less edge on, as we see in the bottom curve here indicated with 0 degrees, then this anisotropy factor can be up to a factor of 10. Here we see the 4 different models I mentioned, the smooth tapered disk of Efstathiou and Roland-Robinson in the top left, the flared disk of Fritz et al. On the top right, the flared two-phase model Skertor of Stalewski et al., and the model of Siebel-Morgan et al. In the bottom right. Okay, here I demonstrate this anisotropy factor I just mentioned. Here we computed this factor for different values of the parameters. And on the left, I have the plot for the Cygnus, the tapered disk model of Efstathiou and Roland-Robinson 95. So as you can see here, this anisotropy factor, as I said, can reach about a factor of 10 or more when you look at high inclinations, about 70 to 80 degrees. And interestingly, for very face-on views, this factor is less than unity. So effectively, quasars are maybe up to a factor of 2 less luminous than they appear to be according to this prediction. This is a feature of all of the models. And to illustrate this, I have a similar plot for the Skertor model on the right. Because the Skertor model is two-phase, has less anisotropy. So at high inclinations, alpha is reaches values of about 7 or 8. But for face-on values, it can still be about a factor of 2 less than unity. It's important to, in this SI, as I said, we incorporate a component of polar dust in CD fitting. And this is because this is an essential component because it can make a lot of difference in cases where it's especially prominent. The presence of polar dust was inferred in AGN from the early 90s. There were 2 key papers by Cameron et al. And Bratz et al. And as I said, we have a simple model for modeling this effect. Models for spheroidal and disk galaxies, we have again, it's probably best to illustrate this with this diagram here. Again, here we have these 2 basic different geometries. On the geometry on the left, which is spherical, so we have stars and dust mixed in the galaxy. We assume the Vauquelins profile for the distribution of both the stars and the dust. And we also have molecular clouds, of course, because in the first few million years after the formation of stars can still be embedded in the molecular clouds in which they form. And as I said, we develop a library for this component. We have 3 parameters. We have the optical depth of the cloud. We assume a delayed exponential star formation history. So we have the time constant of the exponential as a parameter. And we also have as a parameter the intensity of starlight. And we generate a library for this component for different redshifts. Because obviously for a spheroidal component, it matters. You partly see the stars, therefore it's important to have the right age for the stars. On the right, we have the geometry for this component. Again, we have these 3 parameters: the delayed exponential, time constant, the optical depth of the disk, the equatorial optical depth, and the intensity of the starlight. In this case, we assume a double exponential for the distribution of stars, dust, and molecular clouds. And in addition, of course, here we have the inclination of the galaxy. Okay, so now discussed a little bit about the models we use here. I'm going to say a few words about our method, the Markov Monte Carlo method we are using. We developed 2 different codes. The first code is called SARMC+, and it's an adaptation of a code developed initially by Johnson et al. In 2013. It's a code that uses the Metropolis-Hastings algorithm. Okay, and the second code we developed is called SMART. It's a code developed by Harlambia Varnava and myself, and it uses the MC code for the sampling, which we find it makes it more it makes it faster. Another important novelty of our method is that we can incorporate the Spitzer spectroscopy, but at a reduced resolution, which is comparable to the resolution of the radiative transfer models. As I said, we include 4 different models for the AGN torus, and in addition, we have 2 different options for the host galaxy. So in effect, we have 8 different combinations of models we can explore here. And as I said, this method runs in comparable time to popular energy balance methods. We can fit a galaxy in about 1 or 2 minutes, depending on the number of processors you have in your PC. The method is parallelized. So we see a schematic diagram of the approach here. We have, of course, our data. We have libraries of AGN models, starburst models, host galaxy models. We fit these into the MCMC engine, which is either the Metropolis Hastings algorithm or the MC code. And once we get the best fit, we can extract physical, with post-processing, we have a separate post-processing routine. We can extract physical quantities like luminosities, star formation rates, stellar mass, AGN fraction, taking into account this anisotropy correction I mentioned, and so on. So here we see some examples of fitting luminous infrared galaxy. This is from a paper by Herrero, Iana et al. 2017. And you can see the separation of the SEDs into the 3 different components. With red, we have the starburst component. With blue, we have the AGN component. And with yellow, orange, we have the spheroidal component. And we can infer, you see on the right, the luminous, the key components which are of interest for studying galaxy evolution. Another important approach application we had with this method was to detect and characterize tidal disruption events in galaxies like ARC-299. We discussed this in a paper in Science led by Seppo Mattila, Perez Torres, and myself, where we could actually see the emission from polar dust being boosted by the tidal disruption event shown by this orange curve here, in addition to the starburst in red and AGN torus in blue. Okay, I'm going to discuss some models from the HERschel ultraluminous infrared galaxy survey, HERUS. This is a sample we studied with the HERschel Space Observatory. This is a project led by Duncan Farah at the University of Hawaii. And with HERUS, we assembled data for 42 local ULIRGs from the radio to the X-rays, including Spitzer spectroscopy. And this sample includes all of the famous objects like ARC-220, Markarian 231, Markarian 273, and so on. This is one of the galaxies in the sample, which I find very interesting from the point of view of SED fitting, because you can see these galaxies, 2 spiral galaxies, which I'm trying to merge. But on the right, the interesting thing is that this galaxy has a very deep silicate absorption here, indicated by this magenta line here from Spitzer, but no signs of PAHs. And we interpreted this back in 2014 as being an object in which we actually it's an AGN dominated object, but we actually see this object, this torus, almost completely edge on. This is what gives it this very deep silicate absorption, both at a 9.7 and 18 microns. And if referring back to this anisotropy correction I discussed earlier, if you actually do this correction, you find out that this object may be the AGN may be about 10 times more luminous than it appears to be. And this makes this galaxy, if this is correct, if this interpretation is correct, this makes this galaxy about 5 times more luminous than it actually appears to be. And therefore, the most luminous infrared galaxy in the local universe it actually becomes a hyperluminous infrared galaxy. This is a very interesting effect, which it's very interesting to explore more. We see again this galaxy on this slide. We analyzed this. In this plot here, we just did a very simple starburst AGN decomposition. We didn't have the MCMC code in 2014, but now with MCMC code, we did the full decomposition with the starburst, an AGN, and the spheroidal component, and we see basically the same effect. We feed this galaxy with an AGN torus viewed almost edge-on, and we infer similar high luminosity. On the bottom, you see a similar application of the code for R220. R220 is actually a galaxy, is the most difficult galaxy to fit with this approach, which is probably an indication. You can see you don't fit very well the submillimeter. And this is probably an indication that this object is more complicated than our models, for sure. Here we see an example where we feed this ULIRG 10378 plus 1109 with the 4 different AGN torus models. On the left, we compare the whole SED. On the right, you can actually see the feed to the detailed feed to the Spitzer spectrum, shown with the green line. And using this analysis, we can infer which of the models best fits the data. In this case, all of the models more or less fit the data, but this is not always the case. Here we see some results from this analysis of the HERUS sample. On the left, we see a comparison of the observed AGN luminosities by not assuming any anisotropic correction, shown with the green filled circles, whereas the red green circles are the luminosities you get by doing the anisotropic correction. And as you can see, it can be significant for most of these ULIRGs. And on the right, we see the ratio of observed AGN luminosity to corrected AGN luminosity as a function of the corrected AGN luminosity. And you can see this interesting effect that as you increase the luminosity of the AGN, you may have a larger effect. You have more correction, if you like. And this this is something that may be an indication that for more luminous AGN, we may have more geometrically thin tori, which give you a higher anisotropic correction. Here we see a comparison of the likelihoods from all of the 4 different combinations of the models, from which we can infer that the smooth, these are all relative to Cygnus. You can see that the green and the red lines are the Stalewski-Skiertor model and the Fritz model, which usually give worse fits than the Cygnus, and also the Siebenmorker model. So our conclusion from this is that the smooth taper disk gives a better fit to the SEDs of these objects among the 4 models. Another interesting result we had from the analysis of the HERUS sample of 42 objects, we found 2 objects for which you cannot feed the SED with a single AGN torus model. And the reason is because, as you can see, these 2 objects here, you have a blue continuum. You have which we interpreted as being to the fact that in these cases you have 2 AGN. One you view edge-on, and one which you view face-on. The edge-on AGN gives you a feed to the mid-infrared spectrum, whereas the face-on AGN fits the optical UV spectrum. And this is an interesting prediction. It would be nice to confirm with other observations. Another interesting result, which was published in a companion paper by Farah et al. 2022. Here we, because of this anisotropic correction of the luminosities, we found that 12 of the HERUS ULIRGs show evidence that of super-Eddington accretion. You can see there is a change of the slope. The objects above the dashed line here are these 12 objects which show more luminosity than predicted by the Eddington limit. Okay, moving on to higher redshift. In using the SAT-MC plus code, we modeled with in a study by Gao et al. 2021, we modeled about 526 hyperluminous infrared galaxies with both Cygnus and Sigal. And okay, this allowed us to compare the results with the two approaches. On the bottom, there is probably good agreement in terms of luminosity, luminosity and so on. But if you look into the detail of how the stellar mass predicted by the two methods varies as a function of redshift, we found that Cygnus gives you lower stellar masses relative to the main sequence compared to Sigal, and this may be interpreted that you see in these very luminous, hyperluminous objects at high redshift more strongly the effect of quenching of the star formation by the AGN. This is from a study we've done in our group led by Papadopoulos et al., our PhD student, where we fed the SEDs of 200 HELP galaxies at redshift 2. We fed these galaxies with 8 different combinations. All of these 8 different combinations of models, 4 AGN and 2 host galaxies. And we find that these galaxies lie above the main sequence, and they are preferentially fed with a spheroidal model, which is an interesting result. On the right, we've done a comparison of the star. All of these galaxies were fed with Sigal within the HELP project. So on the right, we carry out a comparison of the star formation rate, the stellar mass, and the AGN fraction between our estimates and Sigal. We see that Sigal probably underestimates the star formation rate, especially if you assume 100 megayears averaging, not so strong effect for 10 megayears. It overestimates the stellar mass, and again, it underestimates the AGN fraction because probably doesn't include this anisotropic correction. So this is the kind of analysis we plan to do more, plan to study a bigger sample to see what difference it makes to study these galaxies with a more elaborate method like the one we are assuming here. There's another high redshift example. This result was just published in monthly notices led by Varnava et al., our PhD student. Here we studied a galaxy at redshift Z equal to 6.853. It lies in the Cosmos field. This is the galaxy known as COS 87529. And we studied again this object with these 4 different combinations of models. We find that the smooth taper disk model gives the best fit. Skertor is a little bit behind, but the other 2 models are doing a bit worse. So this allows us to infer the best possible, the best obscurer geometry for this object. We found by doing all of these corrections for the luminosity, calculating the stellar mass, the star formation rate, self-consistently from these fits, we find that we have a 50% more luminosity, AGN luminosity, which translates into a higher black hole mass and a higher star formation rate compared to an approximate method by this object was discovered by Ensley et al. 2022. And finally, moving to the end of my talk, I would like to talk a little bit about an interesting result we get from a galaxy observed with JWST. Sears DSFG1 was initially thought to have a photometric redshift greater than 10, but Zavala et al. Using data from NOEMA found that the redshift is lower, is actually 5.1. Now, what do we try to do in this case? SADMC Plus actually has the option to predict the photometric redshift for this object using, simultaneously with doing the SED fitting, you can determine the photometric redshift. And once we did this, we found that the photometric redshift may be slightly higher than the one inferred by Zavala et al., 5.635. Another interesting thing we explored, you can see the best fit on the bottom left here, where we have a combination of a starburst in red and the spheroidal component in orange. Another interesting effect here is that we try to explore whether you can fit this object purely with a spheroidal or a disk model. And we find that you underpredict the far infrared data, the rest frame far infrared if you do this. So it's a combination of a starburst and a host galaxy gives you a better fit. And we found that if you actually do this, then we inferred that the star formation rate for this galaxy, as you can probably see on the table I have from the bottom, may be up to a factor of 10 higher because if you attribute most of the submillimeter emission rest frame far infrared to a starburst, you may have a much higher luminosity than if you try to fit this with an energy imbalance with just a host. This is a very interesting result we plan to publish soon. And now I would like to say a few words about how can machine learning help in all of this. We are exploring this in the Cygnus Plus project we are pursuing at the moment. For the spheroidal component, as I said, for the spheroidal component, we currently have only 3 parameters. The delayed exponential parameter, the intensity, and the optical depth. We assume a single metallicity, which is assumed to be constant in the history of the galaxy. This limits the application of this model. So what we are trying to do here is to add more parameters in the model. Now, in this case, you cannot have a library because it gets too big. So what we are trying to do is to see if we can accelerate the computation of the model using machine learning. We're using a code called March, which was actually developed for studying the exoplanet atmospheres. We are adapting this for radiative transfer models for galaxies. And we find some interesting results that we can compute the spectrum of a spheroidal galaxy, assuming more parameters in a fraction of a second, whereas in a normal calculation of this model needs of the order of 10 seconds. So this looks to be an interesting approach for accelerating the calculation of the models to feed into these SED fitting codes. Some ideas for further development. We have a lot of ideas for further development. As I said, a main limitation is that we would like to add more parameters to the host galaxy model, and including a parametric star formation history, a non-parametric star formation history, sorry, and the variation in the metallicity history. And this may be probably be done by exploiting AI. Another limitation is that we don't model nebular lines and continuum, so we plan to incorporate that into our code. Another development will be to model X-rays in a similar approach adopted by XCAL. We could add more models, for example, the starburst model of Siebenmorgen and Krugel, and more AGN torus models like Clampy, the model of Honig et al. There are a number of different AGN models we could add. We could add an energy balance option for the host galaxy so that one can self-consistently in the same model using the same approach to compare the two methods. Whereas at the moment we compare results with another code which may have other assumptions and so on. And we plan to develop a more user-friendly interface for the code using a graphical user interface. So as a summary, I would like to say that to study galaxy evolution, we obviously need lots of multi-wavelength data, but we have a lot of data at the moment. We also need models for the emission of galaxies and methods for comparing the models with the data. We demonstrated that it is entirely feasible to feed a large samples of galaxies with an MCMC code that uses exclusively radiative transfer models. Our method allows us to feed an SED with a number of different AGN models, and therefore constrain the properties of the obscurer. And machine learning promises to be very useful for making more progress in this effort by accelerating the calculation of the radiative transfer models and incorporating more parameters. I just finished with a slide that gives information about the publicly available code SMART, developed by Carla Pia Varnava and myself. It's available on GitHub. And to give you an indication of the group that carries out this work, the HERschel Research Center at European University Cyprus. In the first row here, you see the faculty members of the group, and at the bottom, you see our researchers and PhD students. Thank you very much.
Yep. Thanks so much, Andreas. Just put this gallery. Okay, thank you. So we have some time for questions. So
you want me to stop sharing, Ignacio?
That's okay. I think for the time being, just in case you want to show some slides. So
yeah.
So Ralph, do you want to? Okay, because so whoever wants to ask, please just unmute yourself and you can ask. Yeah, we can do it this way. So in the meantime, I was wondering, just out of curiosity, so you're mentioning that the standard methods use this so-called energy balance, whereas you're using a radiative transfer. So could you consider situations where your method, which in principle appears to be more generic, would be okay, whereas the other method would fail? So could you consider that, or it is always going to be somehow an equivalent version?
I think, well, if you are just fitting photometry, it's hard for a method to fail. All methods can give you a fit. SICAL, for example, cannot incorporate this Spitzer spectroscopy or incorporated. It's not designed for that. But for fitting broadband SEDs, both methods can give you a result. So it's just a question of whether the estimated quantities, the estimated physical quantities, are which is the best estimate. This is the difference, as far as I can see.
Okay. So Almudena, you had a question?
Yes, I have a question, a comment, a question. Thank you very much for the talk. I fully agree that the multi-wavelength approach is the best to understand the whole galaxy. But you are very concerned indeed for the AEN contribution. And something that I have learned over the years is that from the project PASSEC, where we study the core of galaxies, normally nearby galaxies at PASSEC scales over the entire electromagnetic spectrum, is that when you do that, the shape of the spectrum changes dramatically, the core change dramatically from the one you will infer from normal resolutions. And even worse, when you compare different missions, different data from different missions, we have different resolution. Not only that, it's also the power of the core change. And that is a bit in line with what you were saying, and for some cases that the core extraction at PASSEC scales shows that we overestimate in many cases the volumetric luminosity of a source by even order of magnitude. But I was a bit more concerned about the shape. So I just wonder whether, given that we have done this analysis from different type of galaxies, type 1, Cipher 1, Taper 2, quasar, quiescent objects of different level of activity, black hole mass, because it changed, whether this modeling that you are doing had to be more for the AEN approach to these cores where are genuinely sampled, and then use this perhaps as an input for general modeling of the galaxy, where you have also the starburst, the AEN, but generally sample, and the host, which also is another problem. We also found that the host could completely, if you do a PASSEC scale, you realize that the host might completely dominate USCD. You don't see the AEN directly. Or
Yes,
you have
okay.
a star formation at the center, you don't see the AEN. So if you try to model that, you will never see the real contribution because the shape changes.
Okay, that's a very interesting point. Of course, I have work going back to 95, where we modeled the nucleus of NGC 1068, where you had the data and had a model just for the nucleus. And of course, now with James Webb, we have good data for high resolution. And one of the challenges here is to model that data. I agree entirely with you. That's something we should do. But it's also important to see if you see the same thing. Okay, you're right. I agree that if you have a weak AGN in a luminous host galaxy, it's very hard to see it. I mean, you see here we are concentrating in objects which are more in ULIRGs, where you have a significant contribution from an AGN. But I agree that you need to combine the two approaches. You need to study where you have good data, high resolution, to study that, to infer the properties of the AGN, and then to see, it's an interesting project to see what do you infer if you study the whole SED for the whole galaxy. Yeah, it's an interesting project. Yeah.
But even if I might say just shortly, even for 1068, if it's a middle type luminosity, we did that. It's one of the first objects we published in 2010. Is where you see immediately that the shape of the spectrum is different at PASSEC scales, and we overestimate by order of magnitude. The observation.
I don't understand on what scale. On what scale is it different?
Sorry.
On what scale is it different?
Scales of a second, particular or more, because then we compare with the Spitzer data. We have adaptive optics and diffraction limit data in the mid and near infrared. and then HST, etc. So we compare the highest angular resolution available, and then you see that the spectrum is very different. You can go on Prieto et al. 2010, you will find it. It's a scale of, it could be even more than 8 seconds, comparable to a Spitzer. It's even worse because the spectrum changed there even more.
Well, my recollection of JWST 1068 is that it's about a couple of 200-300 parsecs. That's within a few arc seconds. Yeah, so you need to study that central region to fit the complete AGN torus. If you go to smaller scale, you see only part of the torus, so you need a more elaborate treatment to compare with models. So you need to incorporate the whole torus in your beam for sure to be able to
I know, but that's
compare with
incorporated for sure in what I have for sure.
Yeah.
Yeah, that's. I guess this is what happens with these systems are really so complicated that in principle it's always So I mean, going in a different direction, but you're mentioning the radiative transfer, the effect of the dust. So your models, are they capable of producing like predictions for the dust composition? I'm mentioning this because a few years back there was some work where there was the analysis of the dust extinction. And what was found is that rather than having the standard typical law that everybody was using in the optical, I mean, for instance, you have a Calzetti extinction law, a wide range of values were found. So is this something that you have considered in the analysis? Can you produce that from the models?
No, in all of these models, we compute a library with a single AGN torus model. Using this AI approach, in principle, you may be able to add the dust model as a parameter, if you like, and explore
Both
that.
for the AGN and the star forming site. So I'm mentioning both as well. So also in the starburst.
Also for the starburst, for the AGN is more difficult because you need to compute the library. It's very computing intensive to compute the library, but there are a number of different libraries. There is one published recently which explores different sizes for the grains. And this is one of the libraries we plan to incorporate, yes, in our project.
Okay. Another just interesting thing I will mention is that I caught my attention what you were mentioning about the derivation of stellar masses and the significantly large discrepancies. So I would like to know what your opinion is, because sometimes there are some papers that claim that in principle the problem of extracting a stellar mass from a photometric set of observations from a spectral energy distribution, that is more or less a done deal in the sense that you can get uncertainties of order, I don't know, at the level of 0.1 dex, perhaps 0.15 dex. So what's your opinion on that? Would you say that's okay, or is it still an open problem?
I think the difference we have here with Sigal, I think, is because in our approach we include this starburst component, which accounts for some of the luminosity which Sigal attributes to the host galaxy. So I think this is the main difference because if you're trying to explain more from the host galaxy than you should, then this gives you you need more stars to do this. So I think this is where we could improve with our method, is that because you are including a more physically motivated model, you have the molecular clouds, you have our model for the starburst is by no means perfect, but it's an attempt to model the emission from molecular clouds, optically thick molecular clouds. By including that, you're bound to do a better job. So this could explain some of the discrepancies. Now, there are, of course, discrepancies with the IMF and so on, but this is the comparison I showed you was converting everything to the same IMF.
To the same IMF. Yeah. Even in that case, that's very interesting. I think that I found that quite surprising. So any other questions? Okay, so I will just, being the chair here, I'm going to abuse just one final thing. I noted that when you're actually parameterizing the star formation histories, you're using a method that basically assigns some parameters rather than having a full stochastic method. Many people these days end up using stochastic star formation histories, most of them derived from simulations. So what's your thought of that? Would you say that this is one of the things that perhaps should be changed, or are you happy with the use of parametric star formation histories?
No, I think, as I said, this is one of the things we would like to improve here. This is
Okay.
my first point here.
Mhm.
And this is something we can do with, I'm very confident we can do it with AI. We are actually running a project at the moment to do this.
Okay.
We can definitely include the non-parametric star formation history. And this is something that could make a difference in the stellar mass. Yeah.
Indeed.
Okay. Yeah.
Yeah. Excellent. So, well, I guess there are no other questions then. If not, I will really thank so much, Andreas. It was a really nice talk. That was very, very nice. And yeah, thank you. Thanks so much for doing this
Okay.
talk.
Thank you very much for the opportunity to give this talk to this very interesting audience. Thank you very much.
Thank you. Take care. Bye-bye.
Bye-bye.